For as long as we have looked up at the night sky, we have asked the most fundamental questions. Where did all of this come from? How long has it been here? For decades, science has provided a remarkably consistent answer. Based on a mountain of evidence gathered over nearly a century, we came to believe the universe was approximately 13.8 billion years old. This wasn't a number plucked from thin air. It was a cornerstone of our understanding, a foundational pillar of modern cosmology. It emerged from meticulous observations of the universe's expansion, traced backward in time to a single, infinitely dense point, the Big Bang. This age defined the cosmic calendar, setting a strict limit on how and when everything we see today could have formed. This 13.8 billion-year timeline became the box within which all of our theories had to fit. It told us how long it should take for the first stars to ignite, for those stars to forge heavier elements, and for those elements to coalesce into the magnificent spiral and elliptical galaxies that populate the cosmos. The discovery of the cosmic microwave background radiation in 1964, the faint leftover heat from the Big Bang, was the triumphant confirmation of this expanding universe model. It was like finding the echo of creation itself, and its properties helped us fine-tune our cosmic clock with incredible precision. Every new piece of data, from the Hubble Space Telescope to ground-based observatories, seemed to reinforce this narrative, giving us confidence that we had a solid grasp on the grand story of our universe. Within this framework, there was a clear and orderly sequence of events. The first few 100,000 years were a hot, opaque fog. Then came the Dark Ages, followed by the cosmic dawn, when the very first stars, known as population 3 stars, flickered into existence, burning off the primordial mist and making the universe transparent. These early epochs were thought to be slow and tentative. Galaxy formation was a gradual process, a cosmic construction project that took billions of years. Small, clumpy, irregular proto-galaxies would slowly merge and grow, eventually sculpting themselves into the grand structured galaxies we know and love today. Our own Milky Way, for instance, was thought to be a product of this long, patient cosmic evolution. This established model, known as the Lambda CDM model, has been extraordinarily successful. It explains the large-scale structure of the universe, the abundance of light elements, and the nature of the cosmic microwave background with stunning accuracy. It has been the bedrock of astrophysics, the lens through which we interpret every new observation. But science is not about holding on to old ideas for comfort. It's about challenging them with new evidence. We built our most powerful tools based on the predictions of this model, designing them to peek into those very first moments after the Big Bang. And now one of those tools is sending back postcards from the edge of time that don't quite match the pictures in our old family album. Enter the James Webb Space Telescope, or JWST. Launched on Christmas Day in 2021, this observatory is not merely an upgrade to the Hubble Space Telescope. It is a revolutionary leap in our ability to see the universe. To understand what makes it so special, you have to think about light and time. Because light travels at a finite speed, looking far away in space is the same as looking back in time. JWST was engineered to be the ultimate time machine. Its massive 6.5-meter primary mirror, a stunning honeycomb of 18 gold-coated beryllium segments, is designed to capture the faintest, most ancient light in the cosmos. Light that has been traveling for over 13 billion years to reach us. What truly sets JWST apart is its focus on infrared light. As the universe expands, it stretches everything within it, including the waves of light traveling through space. Light that may have started as visible or ultraviolet from the first stars and galaxies has been stretched over its cosmic journey into the infrared part of the spectrum. Earth's atmosphere blocks most of this infrared light, which is why Hubble, orbiting much closer to home, couldn't see it as clearly. JWST, however, orbits the Sun 1 million miles away from Earth, at a gravitationally stable point called L2. This distant, cold, and dark vantage point allows its sensitive instruments to detect these faint, ancient signals without interference, opening a window into an era of cosmic history that was previously hidden from view. The promise of JWST was to witness the cosmic dawn firsthand. Astronomers hoped to see the very first glimmers of light from the first generation of stars and the chaotic assembly of the first infant galaxies. According to our 13.8 billion-year-old model, these early structures should have been small, messy, and primitive. We expected to find the cosmic equivalent of small villages and hamlets, not sprawling metropolises. The telescope was designed to test this prediction, to provide the observational proof that our theories about the early universe were correct. It was built to fill in the missing pages of our cosmic origin story, confirming the slow, steady march of galactic evolution. But from its very first deep-field images, JWST began to deliver surprises. The data that streamed back to Earth was clearer, deeper, and more profound than we could have ever imagined. It was a treasure trove of information from the edge of the observable universe. And nestled within that treasure were objects that, at first glance, didn't seem to belong. Instead of finding only the small, clumpy proto-galaxies we expected, JWST saw something else. It saw galaxies from just 500 to 800 million years after the Big Bang that were shockingly large, bright, and well-formed. The time machine was working perfectly, but the history it was revealing was not the one we thought we knew. Imagine you are an archaeologist who has discovered a previously unknown ancient settlement. Based on all your knowledge, you expect to find primitive tools, simple mud huts, and the remnants of a small, fledgling society. Instead, you unearth the ruins of a complex city with paved roads, multi-story buildings, and advanced metalwork, all dated to a time when you believed humans were still living in caves. This is the exact kind of bewildering shock that astronomers experienced when they analyzed the first deep-field images from JWST. They were staring at what quickly became known as impossible early galaxies, objects that simply should not exist so early in a 13.8 billion-year-old universe. These galaxies were not just big, they were mature. Our models of galaxy formation are built on the idea of hierarchical assembly, where small structures gradually merge over billions of years to form larger ones. A grand spiral galaxy with a distinct central bulge and rotating disk, like our own Milky Way, is a sign of cosmic age and stability. Yet JWST found galaxies exhibiting these very features at a time when the universe was less than 1 billion years old. It was like finding a fully grown oak tree in a garden where you had only planted the acorn a week ago. There simply wasn't enough time, according to our established cosmic calendar, for these galaxies to have gathered so much mass and organized themselves into such complex structures. The problem became even more puzzling as scientists looked closer. Some of these early galaxies appeared to contain more mass packed into stars than was thought possible. The sheer density and brightness of these objects defied expectations. It suggested that star formation in the early universe was happening at a rate far more furious and efficient than our models predicted. It was as if the universe had skipped its awkward teenage years and jumped straight to adulthood. This discrepancy wasn't a minor tweak to the theory, it was a fundamental challenge. The existence of these massive, well-ordered galaxies so early on meant that either our understanding of galaxy formation was deeply flawed, or the universe had more time to get its act together than we previously thought. This is the great conundrum that JWST has presented to the scientific community. The observations are undeniable. The telescope's instruments are exquisitely precise. The galaxies are there. The question is, how? Do we need to rewrite the laws of galactic evolution? Perhaps by invoking supermassive black holes that grew at an accelerated rate and seeded these galaxies? Or do we need to reconsider the very foundation of our cosmic timeline? The presence of these impossible galaxies forces us to confront an uncomfortable possibility that the 13.8 billion-year age of the universe, a number we held as a near-sacred truth, might be wrong. The universe might be older, much older. To understand how we can even begin to talk about the age of galaxies that are billions of light years away, we need to talk about one of the most powerful tools in an astronomer's toolkit, Redshift. At its core, Redshift is a manifestation of the Doppler effect, something you experience every day. Think of the sound of an ambulance siren. As it races towards you, the sound waves are compressed, making the pitch higher. As it moves away, the sound waves are stretched out, making the pitch lower. Light behaves in a similar way. When a celestial object, like a galaxy, is moving away from us, the light waves it emits are stretched. This stretching shifts the light towards the longer wavelength, redder end of the spectrum. We call this phenomenon redshift. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that almost every galaxy he could see was redshifted, meaning they were all moving away from us. More importantly, he found that the farther away a galaxy was, the faster it was moving and the greater its redshift. This was the first direct evidence that the universe is expanding. This relationship, now known as the Hubble-Lemaître law, turned redshift into a cosmic measuring tape. By measuring the redshift of a galaxy, we can determine its distance from us and, by extension, how far back in time we are looking. A galaxy with a high redshift is very far away and therefore very, very old. JWST was specifically designed to be a master of redshift. Its powerful infrared instruments can detect the light from the most distant galaxies, those with the highest redshifts ever observed. This is the light that has been stretched the most by the expansion of the universe over its long journey to us. When astronomers say they have found a galaxy at a redshift of, say, 10, they are describing an object whose light has been traveling for over 13 billion years. Our previous age estimate of 13.8 billion years was calculated by measuring this expansion rate and winding the cosmic clock backward to the beginning. The redshift of an object was therefore directly tied to its age within this model. But here is where the puzzle of the impossible galaxies deepens. The redshifts measured by JWST are unambiguous. We know how far away these objects are. The problem is that their physical appearance, their size, mass, and structure doesn't match the age that their redshift implies within our current model. It's like having a birth certificate that says a person is 5 years old, but they look and act like a 40-year-old. You wouldn't question the date on the certificate itself, but you would start to question the assumptions about human development that led you to believe a 5-year-old should look a certain way. Similarly, astronomers are now questioning the assumptions that link redshift directly to age in the way we've always believed. The idea that redshift might be caused by something other than the expansion of the universe is not new. In fact, shortly after Hubble's discovery, a competing theory emerged, proposed by the Swiss astronomer Fritz Zwicky in 1929. He suggested a concept that came to be known as the tired light theory. Zwicky hypothesized that perhaps the universe wasn't expanding at all. Instead, he proposed that photons of light might simply lose energy as they travel over the vast, empty distances of intergalactic space. As a photon loses energy, its wavelength would increase, causing it to shift towards the red end of the spectrum. The farther a galaxy is, the longer its light has traveled, and the more tired it would become, resulting in a greater redshift. For a time, the tired light model was a plausible alternative to the expanding universe. It could explain Hubble's observation that more distant galaxies have higher redshifts without invoking a dramatic beginning like the Big Bang. However, as our observational capabilities improved, the tired light theory began to run into serious problems. One of the biggest challenges came from observations of supernovae. These stellar explosions act as standard candles in the universe, meaning they have a predictable brightness. Crucially, they also have a predictable duration. They brighten and fade over a specific period. In an expanding universe, time itself is stretched along with light. This phenomenon, called time dilation, means that a distant supernova should appear to last longer from our perspective. Observations confirmed this prediction perfectly. Distant supernovae do indeed appear to unfold in slow motion, exactly as predicted by the expanding universe model. The tired light theory, however, has no mechanism to explain this time dilation. If light simply gets tired, the duration of the supernova event should remain the same regardless of its distance. This was a major blow to the theory. Furthermore, tired light couldn't explain the existence and precise characteristics of the cosmic microwave background radiation, which is a natural consequence of a hot, dense early universe that has since expanded and cooled. Faced with this mounting evidence, the scientific community largely abandoned the tired light hypothesis in favor of the Big Bang and the expanding universe. The theory was relegated to the history books, a fascinating but ultimately incorrect idea from the annals of cosmology. It became a classic example of how science works. A hypothesis is proposed, it's tested against the evidence, and if it fails the tests, it's discarded. The Big Bang model, with its expanding spacetime, passed every test thrown at it for decades, explaining a wide range of cosmic phenomena with elegant consistency. It reigned supreme as the undisputed champion of cosmological theories. But the history of science also teaches us that sometimes old ideas, or at least parts of them, can be resurrected in new forms when new, inexplicable data comes to light. The startling observations from JWST have sent some physicists back to the drawing board, prompting them to look for new ways to explain the cosmos. One of the most intriguing proposals comes from Rajendra Gupta, a professor at the University of Ottawa. Instead of throwing out the Big Bang model entirely, He has proposed a hybrid model that dares to blend our established understanding with some of those long-discarded ideas. He suggests that the redshift we observe from distant galaxies might not be caused by cosmic expansion alone. What if it's a combination of two effects, the expansion of the universe and the tired light phenomenon? This new model, sometimes called CC-COTL, covariant coupling constants plus tired light, re-examines a couple of old ideas. The first is, of course, tired light, the notion that photons lose energy over cosmic distances. The second is an even more profound idea, first suggested by the legendary physicist Paul Dirac in 1937, that the fundamental constants of nature might not be constant at all. These coupling constants are the numbers that govern the strength of the fundamental forces, like gravity and electromagnetism. Dirac wondered if these values might have changed over the history of the universe. If these constants were different in the early cosmos, it would have dramatically altered the way galaxies formed and evolved. By combining these two concepts, evolving physical constants and tired light, with the standard Big Bang model, Gupta has created a new cosmic recipe. In this hybrid universe, the formation period for those early galaxies is stretched out significantly. The timeline for the universe's development gets a massive extension. When this new model is used to analyze the data from JWST, the impossible galaxies suddenly become possible. Their advanced state of development is no longer a paradox because in this new framework, they had much more time to grow. And the new age this model calculates for the universe is staggering, 26.7 billion years, nearly double the long-accepted age of 13.8 billion years. This revised age elegantly solves other cosmic puzzles as well. For example, astronomers have long been perplexed by stars like HD 140283, nicknamed the Methuselah star, which appears to be older than the 13.8 billion year age of the universe, a clear impossibility in the standard model. In a 26.7 billion year old universe, the Methuselah star's age is no longer a contradiction. This new model is still in its early days and will need to undergo intense scrutiny and testing, but it represents a bold and creative attempt to make sense of bewildering new data by thinking outside the established box, showing that sometimes the most innovative ideas come from combining the old with the new in unexpected ways. We stand at a remarkable moment in the history of science. The beautiful, coherent story of a 13.8 billion year old universe, a story we have told ourselves for decades, is now facing its most serious challenge. This is not a moment for disappointment, but one of immense excitement. Every time our map of the cosmos has been proven wrong or incomplete, it has led to a deeper, more profound understanding of our place within it. From the shift from an Earth-centered to a Sun-centered solar system, to the realization that our Milky Way is just one of billions of galaxies, each revolution in thought has expanded our horizons in ways previously unimaginable. The JWST's findings are the latest chapter in this grand tradition of scientific progress. They remind us that our knowledge is always provisional, a work in progress, and that the universe is under no obligation to conform to our expectations. Whether the final answer is a 26.7 billion year old universe, a radical new theory of galaxy formation, or something we haven't even conceived of yet, the journey to find that answer will enrich our understanding immeasurably. These impossible galaxies are not a problem, they are a gift. They are clues left by the cosmos, inviting us to look deeper, think harder, and question our most fundamental assumptions about reality. There are still many open questions. If the universe is twice as old, what does that mean for the nature of dark energy, the mysterious force accelerating cosmic expansion? How did the laws of physics themselves evolve, if the coupling constants did indeed change over time? We are like explorers who have just found a new continent on a map we thought was complete. The old world is still there, but now there is a vast, unknown territory waiting to be charted. Future observations from JWST and other telescopes will be crucial in testing these new hypotheses, searching for the telltale signs that can either confirm or refute this new, older vision of the cosmos. This is why science is such a thrilling human endeavor. It is a continuous dialogue between our ideas and the universe itself, with nature always having the final say. The discoveries of the James Webb Space Telescope have ignited a new fire in cosmology, forcing us to reevaluate what we thought we knew and opening up exhilarating new avenues of research. We are living in a new golden age of astronomy, where our view of the cosmos is changing before our very eyes. The universe, it seems, is still full of surprises, and the adventure of discovery has only just begun. The map is not finished, it is unfolding.